of ones. You know this. Nmos is strong passer of zeros but weak passer of ones. So why it is? Anyone? Why it is Nmos strong passer of zeros and weak passer of ones? So I will only tell you the answer. That is, it is strong passer of zeros but weak passer of ones, because for Nmos to turn on, you will apply VDD to the gate, right? You will apply logic 1 to the gate. Logic 1 means it is VDD to the gate. You are going to apply VDD to the gate, and you are going to apply your voltage at the one side. So for example, we'll assume that VDD is just 2 volts. We'll assume that VDD is 2 volts. And you're going to apply VDD here. You're going to apply your VDD 2 volts here. We'll apply here 2 volts. Right? So now, when you apply 2 volts here, when you already you applied 2 volts for the gate, one side you applied 2 volts, that is VDD you have applied, that is logic 1, is nothing but equal to logic 1. Logic 1 means you are going to apply VDD. The 2 volts you have applied. So now what happens when your source, you are connected a capacitor at the source side, you have connected a capacitor. Okay. Now this capacitor is not charged initially, it is 0 volts. So now what happens to your VGS? Your VGS is nothing but equal to, you can write it as VG minus VS. You can write it as VG minus VS. So which is equal to, now what is VG? VG is nothing but your gate voltage, which you have already applied 2 volts. And what is VS? VS is capacitor, which is not initially charged, it is 0 volts. So now your VGS is 2 volts, and obviously this 2 volts is greater than your threshold voltage, VTH. This 2 volts is greater than your threshold voltage, that is your VTH. So we'll assume that the threshold voltage of this MOSFET is 0.7 volts or 0.5 volts. We'll assume it as 0.5 volts. We'll assume it as 0.5 volts. Point 5 volts. Okay. Now, what happens to your VGS? So your VGS became equal to, your VGS now is equal to 2 volts initially when capacitor is not charged. So your VGS is 2 volts. Obviously, when VGS is greater than VTH, your MOSFET is on. Now your MOSFET is on. So because when this MOSFET is on, what happens? Your MOSFET starts conducting. Your MOSFET starts conducting and current starts flowing from drain to source. Whenever you apply higher voltage, automatically that will become drain. Whenever there is a lower voltage, that side will become source. Right? Because current in the NMOS will start flowing from drain to source. Okay. So now as VGS is greater than VTH, why VGS is greater than VTH? Because for gate you have already applied 2 volts as VDD and source is initially not charged, it is 0. So VGS means it is VG minus VS, 2 minus 0 is 2, which is greater than VTH. So VTH is nothing but threshold voltage of this MOSFET, it is 0.7 volts. So because of that, this MOSFET is on, now it starts charging. So when it starts charging, when this capacitor starts charging, now obviously the source voltage, that VS, starts increasing. your Vs starts increasing, right? So it starts increasing from 0 to 0.5 volts. It starts increasing from 0. First we'll assume it is first 0.5 volts. So when it is 0.5 volts, you calculate your VGS. Your VGS is VG minus VS. Your VG is at 2 volts and VS is at 0.5 volts. 2 minus 0.5. So I'm not able to write point annotation. I'm not able to write this point. Okay, so your VGS is 2 minus 0.5 now because your source has charged to 0.5. So 2 minus 0.5, your VGS will become now, which is equal to 1.5 volts. Now it becomes to 1.5 volts. Again, your MOSFET is on. Again, your MOSFET is conducting. Current is flowing from drain to source. Again, this capacitor is charging. The capacitor is charging and its potential starts increasing. So now your Vs now becomes from 0.5, it becomes 1 volt. You assume your Vs from 0.5, it becomes 1 volt. And what happens to your VGS? So now your VGS becomes 2 volts. That is VG is 2 volts. Vs is 1 volt. So 2 minus 1, now your VGS is 1 volt now. So when VGS is 1 volt, still it is greater than VTH. Your VGS is still greater than VTH. Still MOSFET is conducting. So its current starts flowing from drain to source. So again, now as current is flowing from drain to source, obviously capacitor starts charges. Capacitor voltage still more increases. Capacitor voltage is nothing but equal to your source voltage. So now your source voltage will now become equal to 1.5 volts, or we'll take it as 1.49 volts. When it becomes 1.49 volts, what happens to your VGS? So your VGS is 2 minus 1.49. It is 0.51 volts. It is your VGS is now your VGS is now 0.5 volts. At that time, what was the source voltage? Source voltage was 1.49 volts. When source voltage was at 1.49 volts, your VGS is 0.51 volts. Still it is greater than VTH, right? Because I have taken VTH as 0.5. Still it is conducting and current is flowing from drain to source. But when your source voltage becomes just 1.5 volts, your source voltage becomes just 1.5 volts, your VGS becomes exactly equal to your threshold voltage. Your VGS becomes equal to exactly threshold voltage, right? Because your gate is at 2 volts, source voltage is at 1.5 volts. The capacitor is charging. The capacitor is charging. So the source voltage became 1.5 volt, but gate voltage is at 2 volt. So 2 minus 1.5 volt is 0.5 volt. Still it is great. Still it is equal to VTH. Still slightly your MOSFET will be conducting and current will be flowing from drain to source. But when the source voltage becomes 1.51 volts, your VGS becomes 0.49 volts. It becomes 0.49 volts, right? VGS means VG minus VS. VG is at 2 volts and source voltage is at 1.51 volts. So your VGS become equal to 0.49 volts, which is less than VTH. Now your MOSFET ceases the conduction because MOSFET turns off. When VGS becomes less than VTH, you know that MOSFET will turn off and it will stop the conduction. So your source voltage will stop to 1.5 volts it will not go above 1.5 volts, right? Because after 1.5 volts, MOSFET stops conduction. It becomes turned off. No current will flow from drain to source. Here, source voltage stops at 1.5 volts. So what is this 1.5 volts? It is nothing but your VDD, right? So this 1.5 volts is nothing but your VDD. It is VDD minus VTH. This 1.5 volt, but is VDD minus VTH. Right? VDD was 2 volts. That is what you applied. Your VTH, I have assumed it as 0.5 volts. So your source voltage will stop at 1.5 volts. That is what VDD minus VTH. That is, your output is degraded by 1 threshold voltage. Your output is degraded by 1 threshold voltage. Output will not go to complete VDD, right? Output is not going to complete VDD. It is stopping at 1.5 volts, right? This is 2 volts. It is stopping at 1.5 volts. It is not going to complete VDD. So because of this reason, your NMOS is weak passer of ones, even though you're applying 2 volts here as logic 1, but at the output side, we can call this as output side, we are getting only 1.5 volts. If I assume 0.5 is a threshold voltage. Here I have mentioned 1.3 volts because I have assumed 0.7 is a threshold voltage. So it doesn't passes your 1 completely. Logic 1 is not passed completely. Because logic 1 we have assumed it as 2 volts, but here it is only passing 1.3 volts. So because of this reason, your NMOS is called weak passer of 1. But your NMOS is strong passer of zeros. Your NMOS is strong passer of zeros. When you apply 0 here, you have some voltage here. Assume it as 1.3 volts only. So you apply 0 here. At the input side, you apply 0. Here you apply 0. Okay. Now this is at higher potential. This is at lower potential, right? This is at higher potential because you have some logic 1 here. This is at higher potential. This is at lower potential. This becomes source now. This becomes drain. It always flows from drain to source. Now this becomes drain and this becomes source. So your VGS, when you calculate your VGS, which is always greater than when you apply 0 here. I'm speaking when you apply 0 here and you have high voltage at this side. This is always your input side. This is always your output side. Okay. So input side you have applied 0. Here I think you have high voltage. Some high voltage, that is 1.5 volts or 1.3 volts you have. Okay. Now this becomes drain because it is at higher potential. This is becomes source because it is at lower potential because current always flows from drain to source. So now if you calculate your VGS now, this is nothing but equal to VG minus VS. So VG is at 2 volts, VS is at 0 volts. Now this is nothing but 2 volts only. Or means it is continuously turned on because you have fixed your VG to 2 volts and VS to 0 volts. So the whatever the potential you have, whatever the voltage you have, or whatever the charge you have, that will be continuously discharged because this is at 0 volts. Means 0 volt means I can connect this to ground. 0 volt is nothing but a ground. So this whatever charge you have at this side, output side, that will be continuously discharged and output will become 0. And output will become 0. So NMOS transistor totally passes zeros, but it is weak pass of ones. It will not pass ones. When you apply logic 1 to input side, you will not get complete logic 1 at the output side. But when you apply logic 0 at the input side, output will become totally 0 because your VGS is 2 volts, it is fixed. Okay, this is the concept of your NMOS pass transistor. Similarly, you can analyze for your Pmos transistor, but Pmos transistor, you know that the concept is little bit different, right? Pmos, you know that concept is little bit different. What is the concept you have? So your VGS for Pmos to turn on, your VGS should be less than VTH, right? This is the concept. Your VGS should be less than VTH and your threshold voltage will be negative for Pmos. So if your threshold voltage is minus 0.7, your VGS should be less than minus 0.7. Then only this MOSFET will turn on. Okay. Similarly, you can analyze for your Pmos transistor. The concept what I have explained, like this you can analyze for your Pmos transistor, and you always remember that in Pmos transistor, current flows from source to drain, right? Because majority charge conductors in channel the charge conductor are holes, so the current direction will take it is from source to drain. So similarly, you can analyze for your Pmos pass transistor. So your Pmos pass transistor to turn on, we will apply 0 to the gate. For Pmos transistor to turn on, we will apply 0 to the gate. Then only, for example, we will analyze like this. I have applied voltage VDD here. So we analyze like this. I have applied a voltage VDD, that is logic 1. I have applied VDD here, that is logic 1. Right? And I have connected a capacitor which is initially not charged. I connected a capacitor here which is initially not charged. Okay. Now I already told you current flows from source to drain. Now the higher potential vehicle will become source and lower potential vehicle will become drain. Okay, current is flowing from source to drain. So I applied VDD here. So when you calculate your VGS now, VGS, when you calculate now, it is VG minus VS. Your VG is at 0 voltage, so you have 0 here, minus your source voltage is at VDD, that is 2 volts. We'll take VDD as 2 volts. 2 volts. It is nothing but equal to what? Minus 2 volts. This is nothing but equal to your VGS is nothing but equal to minus 2 volts, which is obviously less than VTH. So now your MOSFET is on. That is a condition for your Pmos to turn on. Your VGS should be less than VTH, and your VTH is minus 0.7 volts. We have taken it as minus 0.7 volts, or we'll take it as same as your previous case. It is minus 0.5 volts. Now here you can see your gate is fixed, right? Your gate voltage is fixed, that is 0, and your source voltage is also fixed, that is fixed to VDD. VDD is 2 volts. So now it is minus 2 volts, which is less than VTH. So your Pmos is always on unless and until you are removing your source voltage. So the current flows from source to drain. So the capacitor what you have connected here, that will be charged to the complete high voltage. That will be charged to the complete high voltage, because here what you have is drain. Drain potential is changing. Source potential is already fixed. So this will totally charge to a complete voltage. So when you apply 2 volts here, this will totally charge to 2 volts. Completely charged to 2 volts. Current starts flowing here. Okay, because of that, it is strong passer of ones, but it is weak passer of zeros. But it is weak passer of zeros. So this is your input side. Always is your input side. This is your output side. Your input side and this is your output side. You assume that I have connected volts here and I have applied 0 here. I have applied 0 means obviously this is connected to ground. Because I have connected 0 here. So this is a higher potential now, right? This is higher potential. This will act as a source. This will act as a, because current always flows from source to drain. Now what is your VGS? So your VGS is VG minus VS. So your VG is 0 volts, and I have already assumed you have high voltage here. So I will take it as minus. High voltage already you have that is minus 2 volts. So you will get minus 2 volts, which is less than VTH. Now what happens? Your MOSFET starts conducting and current starts flowing from source to drain. This is source and this is drain. Current starts flowing from source to drain. So your MOSFET starts discharging. Sorry, the capacitor starts discharging. Your capacitor starts discharging. Because of that reason, the source voltage starts decreasing, right? Because capacitor start discharging, this is source now. This side is source. V outside is source now, because that is at higher potential. So your capacitor voltage starts decreasing. So when capacitor voltage starts decreasing, so your VG is already fixed to 0 volts, but your source voltage starts decreasing. So from 2 volts, now it becomes 1.5 volts. So now if it becomes 1.5 volts, now what is the output voltage? It is nothing but minus 1.5 volts. Your VGS is minus 1.5 volts. Still MOSFET is on. Still the capacitor is discharging. So when the source voltage becomes 0.5 volts, you have taken threshold voltage as 0.5 minus 0.5. When it becomes 0.5 volts, then 0 minus 0.5. So it is exactly minus 0.5 volts. So which is equal to exactly minus 0.5 volts. I will write here your VGS is equal to exactly minus 0.5 volts, which is equal to your VTH, right? Which becomes equal to your VTH. So still the MOSFET is in the edge of cutoff region and conduction region. So it will be still conducting. But when this capacitor, what you have, it is still discharging. When this capacitor voltage becomes 0.49 volts, then what happens to your VGS? Your VGS becomes 0 minus 0.49. So it is minus 0.49 volts. Now this became greater than your VTH. Your VTH was 0.5, right? Your VGS became greater than, your VGS now became greater than VTH. So at that time what happens? Your MOSFET stops conduction. So your drain voltage was at 0.5 volts. It will stop at 0.5 volts only. So what you applied here, you applied 0 volts, but at the output side, you are not getting 0 volts, you are getting 0.5 volts, because your MOSFET has now stopped the conduction, because your VTH becomes greater, your VGS becomes greater than VTH. So because of this reason, it will cease the conduction. So your output side, the voltage stops at 0.5 volts only. So here Pmos transistor is strong passer of ones, but it is weak passer of zeros. Even though at the input side you are applying 0, but at the output side it's stopping at some voltage which is higher than 0. It is not becoming completely 0, it is stopping at little bit higher voltage than 0. That is your Vth voltage. Because of this reason, your Pmos transistor is weak passer of zeros but strong passer of ones. So after this, because of this reason, to overcome this reason, what we did is we went with transmission gate. Transmission gate, as I shown here, your Pmos and Nmos both are connected in parallel combination. So your Pmos and Nmos both are connected in parallel combination. So instead of representing Pmos with a bubble at the gate, I have represented by showing the arrow mark at the source side. Instead of representing bubble at the gate, here in this diagram I have represented by showing arrow mark at the source side. Here also Nmos I have represented by showing the arrow mark at the source side. So at the source side, the arrow mark always it is inwards, right? It is inwards, that is towards gate for Pmos, and outwards at the source side the arrow mark is outwards for the Nmos. And substrate connection, substrate of Pmos is always connected to source side and substrate of Nmos is always connected to source side, and Pmos and Nmos both are connected in parallel combination. So this side we'll call it as input V in, this side we'll call it as output V out, and gate voltage for Pmos we'll call it as V in P, and gate voltage for V in that is gate voltage for Nmos we'll call it as V in N. This is the schematic of your transmission gate which you have to draw. This is schematic of your transmission gate which you have to draw. Okay, and you already know that Pmos will turn on when you apply 0 voltage to V in P, and when you apply VDD to V in N. Right? Gate voltage of Nmos should be connected to VDD and gate voltage of Pmos should be connected to 0. Then only your Pmos and Nmos both will be on. Okay, now you assume both are on. Okay, now you assume both are on, that is your V in P is connected to 0 and V in N is connected to VDD. Now both are on. So when I apply V to logic 1, logic 1 means it is VDD. When I apply V in is equal to logic 1, that is equal to VDD. Now what happens? Your Pmos and Nmos initially both are on, both will start conducting current. So at the output side I have a capacitor. Capacitor starts charges. Both are conducting now. Capacitor starts charging. When this capacitor voltage becomes, so VDD will assume it as 2 volts. When capacitor voltage becomes equal to 1.5 volts, your Nmos ceases the conduction, right? Because it is a weak passer of ones, I have explained you. Your Nmos ceases the conduction, stops the conduction. But still your Pmos is on, it will continue the conduction. So your output voltage will reach to 2 volts. So when one stops the conduction, other takes in charge of continuing the conduction, and your capacitor voltage will reach to complete 2 volts. It is complete VDD. So this is how you are going to get the complete logic 1 by using your transmission gate. Now you assume that your output is at 2 volts and you applied V in is equal to 0. Now you applied V in is equal to 0. Now both starts conducting like this in reverse way. Okay. Both starts, so your output is at 2 volts and input you applied 0. So both starts conducting in this way as I explained before. Now what happens when your output reaches to 0.5 volts? Your PMOS stops conducting. It ceases its operation. It stops conducting, but still your NMOS is on. I've explained before. So it's still it is on. It will take care of completely discharging this point. So this even 0.5 volt is completely discharged and output becomes 0. So when you apply input as 2 volts, output becomes completely 2 volts. When you apply input as 0 volts, output becomes completely 0 volts. This is how the switching action correctly takes place in case of transmission gate when both V in P and V in N both are on. That is V in P and V in N both if you apply for V in P if you apply 0 volts and V in N if you apply VDD, PMOS and NMOS both are on. At this condition, the output will become completely logic 1 when you apply input logic 1, and output will become completely logic 0 when you apply input 0. Okay, this is about transmission gate. This is the operation of transmission gate. So now, sir, Arvind sir.
Yes, Deepak, I'll take over.
Sir, shall I continue or you will take over, sir?
I'll take over. You can stop sharing the screen. I'll start sharing.
Okay, sir. Thank you.
Okay. Hello, students. I hope the screen is visible to you. Okay, till now Deepak had explained about the working of the transmission gate, how NMOS passes good 0 and PMOS passes good 1. And you can see the connections here. The substrate of the PMOS is connected to source and the substrate of NMOS is also connected to source. That is, as usual, the connections are that way. You are already familiar with these connections. Now the source of PMOS is connected to the drain of NMOS and the drain of PMOS is connected to the source of NMOS. Actually, until we connect them, source and drain are physically same and they are interchangeable. Only when we make those connections, then we call these terminals as source and drain. Regarding this also, I had already told earlier in the class on inverter. So now, before proceeding for the layout of this circuit, I want to conduct a small viva. As Deepak has explained in detail about how Pmos passes good 1 and Nmos passes good 0. Now for the same purpose, we write Pmos at the top and Nmos at the bottom in case of the regular static Cmos gates. We have been working with static Cmos, inverter and NAND gate and NOR gate till now. And you already know that always Pmos is at the top and Nmos is at the bottom. The reason is this, that Pmos passes good 1 and Nmos passes good 0. Now let me conduct a small viva. The first viva question to all the students who are right now present here. How many are here? There are 13 students now. My first question to the students is, what may be the use of this transmission gate? Why should we connect this transmission gate this way? And when we are able to connect Pmos and Nmos for regular inverter, NOR gate and NAND gate, we can use the same configuration for obtaining other logic functionalities. Whereas this transmission gate, it is simply passing whatever is the input to the output. It is not an inverter. Now for that matter, it is not a buffer also. If at all we want a buffer, let me write a buffer. If at all we want a buffer, we should have an inverter and we should have one more inverter. My question is, can we use a transmission gate as a buffer? That is my question. Now this is the transmission gate. This is now the transmission gate. So in place of a buffer, which is basically two inverters connected, can we use the transmission gate as a buffer? Someone should answer.
Sir, is your question why transmission gates, or can we use transmission gates as a buffer?
Yeah, both way. Both way. Why transmission gate? That is the first question. Let us say. The second question is, can we use the transmission gate as a buffer? Any answers?
We are using this transmission gates because like earlier, like in NMOS and PMOS, we had this strong 0, weak 1 kind of concept, but now we do not have such kind of concept in transmission gates, according to me. I think that is one of the reasons why we are using transmission gates.
Okay.
Then the next question was, can we use transmission gates in place of buffer? Because transmission gate does not act like an inverter, I think we can use it.
Okay.
With little modifications here and there, I think.
Okay. But transmission gate cannot be used as a buffer. This cannot be used as a buffer. The reason is
it cannot cause delay or something like that.
Tell me.
Like buffer is used when we want to create a delay, I think, and this does not create that or something like that.
No. It is not related to delay. We do not want delay actually, right? Basically, buffer is what? Buffer is going to give a current drive. When you give an input signal, let us say I write a buffer like this. Now this is the buffer. Now this is a buffer. Now when you give a signal here, let us say the signal is slightly weak. Now at the output, signal will become stronger. That is one reason. The level of the digital signal is retained at the output. How? Because the buffer has a VDD here. Buffer has a VDD and a ground. So that input signal, when it is coming inside the buffer, from the VDD it is going to take the power. Even in case of these inverters, there is this VDD here. For both these inverters, there is this VDD and ground. So whenever input signal is coming, you have to visualize the inverter with one Pmos and Nmos there. So as soon as the input signal is there, accordingly either a Pmos will turn on or a Nmos will turn on. When the Pmos is turning on, it is taking power from this power supply, and that power is transferred to the output. So for the buffer, the current and the voltage is coming from the power supply, not from the input. So basically a buffer is what? A weak signal is made as a stronger signal, both in terms of voltage as well as current. So this voltage and current is coming from the power supply. That is the purpose of buffer. Now in case of this transmission gate, you cannot use it as a buffer. The reason is input is passed over to output, that's all. This circuit does not have VDD at all. The circuit does not have power supply at all. When the circuit is not having a power supply, the weak signal, if input is a weak signal with weak current itself is going to be passed over to the output. Only thing is Pmos will pass 1 and Nmos will pass 0. Pmos will pass strong 1, Nmos will pass strong 0. That's all. Otherwise, this is not a buffer. So transmission gate cannot be used as a buffer. I hope it is clear. Now, if transmission gate cannot be used as a buffer, what is its use? Because simply input is coming to the output. If weak input is there, that will remain weak even at the output. Only thing is, logic 1 will pass through Pmos, logic 0 will pass through Nmos, that's all. Otherwise, signal's power will remain the same here, because there is no power supply at all in this transmission gate. So what may be its use now? Any answer?
So transmission gates are used to like make any digital things. Like that's what we learned last semesters. We made gates using transmission gates and all, like
Yes.
and or NAND,
Yeah.
such kind of things we can make using transmission gates. So
Yes.
whatever we are trying to build now, or like digital designs, we can do that using transmission gates.
Yes, that is correct. Using inverter and using NAND gate and NOR gate, you can implement complementary logic. In the sense, with the regular static Cmos circuitry, there is always a complemented output. And if you want to implement AND gate or OR gate, that is not possible directly using static Cmos. Whenever you want to have an AND gate, you have to construct a NAND gate, then you have to connect one inverter. Same case with a NOR gate. But for XOR gate and XNOR gate, you can directly implement using static Cmos only. So that way, the complemented logic is directly possible with the static Cmos. That means whatever circuit you have been studying till now, that is static Cmos. But the direct logic of and OR is possible using transmission gate. So Kuldeep has given the answer. It is easy to implement a latch and flip-flop. I cannot completely endorse this answer, because using static Cmos also we can implement latch and flip-flop, not just using transmission gate. And Kuldeep has also given the answer, we can implement AND logic gate. Correct. AND gate and OR gate can be implemented directly using transmission gate. So those who are keen on learning VLSI, if at all you have to increase your skills in the field of VLSI, in the next semester, you can take up some mini project. In the mini project, you can implement a full adder using transmission gate only. There are enough publications there. You can search in either IEEE Explore or in other journals or conference publications, where there are many people who have already worked on transmission gates. Or else you can refer to the textbooks which were prescribed for post-graduation in VLSI design. There are many textbooks which are part of MTech syllabus. In those textbooks, there are implementations of transmission gates for adders, different types of adders, or even for multipliers using the adders. So those who are very keen or those who like this particular VLSI design, in the next semester, you can plan for implementing in your mini project one of the bigger electronic designs, some digital designs using transmission gate. Okay, so using transmission gate, it is possible to implement the logic functions which we have been implementing using static Cmos also. Even though it is simply the input coming as output, with the different combinations of these transmission gates, it is possible to implement the other logics. Okay, that is the answer. Now the next Viva question is, if we can use transmission gate, then why are we using the static Cmos? I have already given you the answer earlier, because in the static Cmos we have power supply. In the transmission gate we do not have power supply as such. So input simply passes to output, that's all. But if at all we want to have a drive, current drive or a power drive, it has to ultimately the output signal has to drive the load. For giving the current drive, again we have to go for static Cmos. So normally what we do in the industrial applications is we will combine both of these. Wherever required, we will use static Cmos. Wherever required, we will use transmission gate also. We will combine them together. You might have already studied the circuit of latches and flip-flops in the theory classes. There you would have seen that there will be an inverter also, there will be a transmission gate also together. And that is how you form a flip-flop. Let us say, let me write that circuit here. I hope you have gone through this circuitry of you have a transmission gate, and then you have an inverter, and cross-coupled inverter you will have, and then you will have a connection like this. Which means using this transmission gate, we are deciding upon whether to inlet the signal or not. Just like we have a security gate at the campus, or just like we have a main gate at your house. Now at the security gate, the security people check every person about the ID card and whether the authorized entry is there or not. Based on that, they will allow inside. Same way, using transmission gate, the inlet of the signal can be controlled. Now later on, the same signal can be stored by means of this particular cross-coupled inverter. Now, if there is a weak signal coming here, that weak will become anyhow strong by using the inverter here. The only point is you will have a inverted output form, because if at all this is D here, you will have a D bar here. That logic state has to be taken care in the design. Now this is one particular latch. Now this particular latch can be made as a flip-flop or like a master slave flip-flop by connecting one more same circuit at the next part. By connecting one more transmission gate here and by connecting again cross-coupled inverter at the other side. Only thing is the gate control for this transmission gate and the gate control for the other transmission gates have to be complementary. Means, let us say if this is G, then for the next transmission gate it has to be G bar. That is when the same circuit works as master and slave. This circuit is master, the next succeeding circuit is slave. That way we can construct latches and flip-flops using transmission gates as well as using static Cmos. That is the usage now. That means in the real applications, we use transmission gate wherever we want to have that advantage. Now my question again is, What is the greatest advantage of the transmission gate now when compared to static CMOS? Can anybody answer? What is the greatest advantage of transmission gate when compared to the static CMOS? No answer?
Something related to power or something.
Yeah,
Because in
it
theory class we learned it as
is
power.
related to power. But what is it? It is related to power only. But what is it?
It increases the power.
No,
Dissipation or decreases.
no, there is no power dissipation at all.
We learned something about power in theory class, sir. I'm not sure about what.
Yeah, but there is no power dissipation at all because in transmission gate there is no power supply at all.
Yeah, so in the other ways there is power dissipation, and this it's not there. That is why this is better.
Yeah. In the static CMOS there is dynamic power dissipation at least. In the static CMOS there is no static power. Kuldeep has given the answer that there is no static power dissipation. Actually there is no power dissipation at all. Neither static nor dynamic. Now in the case of inverter, let me try writing the inverter circuit. See, in the case of inverter, when Pmos is on, Nmos is off. And when Nmos is on, Pmos is off. There is no static power in the case of regular static inverter also. Why? Because there is no connection from VDD to ground. When there is no connection from VDD to ground, there is no static power dissipation in case of static CMOS circuitry. Even though we call it as static CMOS circuitry or general complementary CMOS, complementary MOS circuitry, there is no static power dissipation in case of regular CMOS circuits. But there is a dynamic power dissipation, which means when PMOS is on, it is going to charge the load capacitance at the output. So there is a dynamic power dissipation in case of regular CMOS inverter. There is no static power dissipation. That is the advantage of CMOS when compared to BJT. Because in BJT there is a static power dissipation. Let me write BJT circuit. So in the case of this BJT, we have a base resistance, we have output at the collector, we have emitter grounded, and we have VCC. Now in the case of BJT, when the transistor is on, current is flowing from VCC to ground. When there is this is high, when the transistor is switched on, current is going from VCC to ground. When the transistor is off, current is going from VCC to load. This is in the case of BJT. But in the case of CMOS, when PMOS is on, NMOS is off. Okay, you can see that in BJT, there is a static power dissipation also, there is a dynamic power dissipation also. Both are there. Dynamic means when the signal is low, power is going to the load. When the signal is high, input signal is high, there is a power which is going to ground. And there is a load getting discharged to ground also. Static power dissipation basically means from VDD to ground or from VCC to ground, if current is flowing, there is a wastage of power there. That is called static power dissipation. But in BJT, static power dissipation is there. But in CMOS inverter, static power dissipation is not there. From VDD to ground, there is no current flowing at all, except in that region C. You already studied the transfer characteristics of inverter. In region C, we have a small amount of dissipation from VDD to ground when both are partially on. When both PMOS and NMOS are partially on. Otherwise, in regular CMOS inverter, there is no static power dissipation. There is only dynamic power dissipation. But in the case of transmission gate, there is no power dissipation at all. Means, in this circuitry, you will not see any power supply at all. It is the recombination of input signals itself in many different ways. We are going to implement the logic circuits. That's why I had told you that you can take up a mini project in the next semester to implement a full ladder only using transmission gates, without using CMOS, regular CMOS circuitry at all. Only using transmission gates. It is possible, people have worked on it. The only requirement there is that the input signals must be strong. Otherwise, the energy of the signals will not be powered up by the transmission gate at all, because the transmission gate does not have a power supply at all. Which means, if at all you construct any circuitry using transmission gate, the circuit will have zero power dissipation. There will be no power dissipation at all. Only requirement is that input signal should be strong enough to pass through the transmission gates. Because even the output signal will have the same power as that of the input signals only. Because there will be no supply of power at all. So that is the advantage also, that is the disadvantage also. Both are there. Advantage itself is the disadvantage for the transmission gate, or disadvantage itself is the advantage in the case of transmission gate. I hope now things are clear. So if things are clear, now the next question is, look at the symbol of the transmission gate. Now someone has to tell me why the symbol of the transmission gate is like this. You will see a bubble there at the top, that is for the P MOSFET. And you will see a regular line at the bottom, that is for the N MOSFET. So these two are for the gates. That is fine. And you have input signal here, output signal here. That is also fine. But this is like a crazy symbol. Why the symbol is like this? As I have been telling you, whoever has invented the symbol is a genius. For example, let us say there is a symbol like this. There is a symbol like this. And below it will be written danger. It will be written danger. It will be written 11,000 volts. Now, when they write already danger and 11,000 volts, why do they put the symbol of the skull and the bones? Now, when they already have written below danger and 11,000 volts, why do they put this symbol skull and the bones? The reason is, if an illiterate person comes, let us say the person who does not know how to read English, even then in that case, color is red, still he may not understand. Now, there is a skull, there is a bone, which indicates that if you touch this 11,000 volts, you will become that. If you touch this 11,000 volts, 11,000 volts are going to burn you out and only your skull and bones will remain. That way, some genius has made this particular symbol of skull and bones. Even though it is funny, it is highly meaningful. So I keep saying that whoever invents these symbols, they are genius people. Whoever made a symbol for transistor itself is a genius, because you can see this transistor, right? You can see this transistor. Now, in this transistor, MOS itself is there, because upper topmost layer is metal, source and drain are metal. So this is now at the top, metal. Then you have oxide, then you have semiconductor below. At the top you have metal, then you have oxide between the gate and the channel, then below substrate is semiconductor, so you have a metal, oxide, semiconductor. And it is a field effect transistor. That way, whoever made the symbol for MOSFET is also a genius. Whoever made a symbol for Bjt is also genius. Now in the MOSFET, source and drain can be interchanged. Only after making connections, you will call the terminal as either source or drain. That means source and drain are not distinguished. That way, the symbol is a genius symbol. Similarly, between the gate and the channel, you have the gap here. That means there's a capacitance at the gate, which is directly indicated. So even though a transistor is simply a connection of some horizontal and vertical lines, when they make a symbol, the symbol indicates the complete character of the device. That way, whoever makes these electronic symbols or any symbols for that matter, I should consider them as genius people. Now, whoever made this symbol for the transmission gate is also genius. Now, you should tell me what is the meaning of this symbol. I have already told you about this bubble at the top. That is indicating only complementation. Whenever we put this bubble or a small circle, that is basically meaning complementation. But otherwise, why this symbol is such a crazy symbol? Someone has to answer.
Is that because we are not doing anything to the input, we're just passing it like that? And then,
Yeah, that is fine. But for that, we can have a symbol like this, no? We can have a simple symbol like this. We can write it like this, no? Right. Because input is...
or is it two NOT gates back to back, so they want to make it compact, so they put one on top of the other?
It is, there is no NOT gate there, right? There are no inverters there. It is only a Pmos and Nmos.
Yes, sir, but then the final output is what the input is. So two NOT gates connected back to back. So they did not want to occupy so much space, so they put one on top of the other. So it became two triangles like that.
No, it is not a NOT gate. It is one device here. See, this triangle is one device. Generally, for the amplifier, we use this symbol, right? This is the symbol used for amplifier, even for buffer. In the analog domain, we use this symbol for amplifier. Okay, you already are familiar with the A by 1 plus A beta formula for negative feedback and positive feedback, Barkhausen criterion. You are familiar. So this is the symbol used for amplifier. Now, what is that amplifier here? One transistor is an amplifier, right? There is another transistor connected with the source and drain in the other way, right? So this basically indicates the two transistors only. You can see here. Now this Pmos is an amplifier and this Nmos is an amplifier. But here source is here source is here. So source and drain are interchanged in case of Pmos and Nmos. Just to indicate that it is just two devices. One device in this direction, one device in the other direction with respect to source and drain. That is how the symbol is designed. Now, some textbooks use this symbol. There are other textbooks which use another type of crazy symbol. For example, Neil Weste uses this symbol. Neil Weste uses this symbol, whereas Pucknell uses this symbol. Whatever you see at the left side, one textbook called Pucknell, he uses this symbol, left side. Whereas in the right side, whatever symbol you see, Neil Weste author uses this symbol. And both are used anywhere. It is up to you to choose any particular symbol. Because there are multiple symbols now for a transmission gate. There are two symbols now. As transmission gate logic is not completely standardized, even now people use either of them. Depending upon which one you like, you can use the symbol. Now, what is the meaning of the symbol at the right side? Symbol at the right side is totally obvious. You can see one Pmos at the top, you can see one Nmos at the bottom directly. So what Neil Weste did was he simply connected Pmos and Nmos in this manner only, regular transistor symbol only. He merged together to get the symbol for transmission gate. Whereas the left side is more attractive. That is why we are using this particular symbol in our labs. It looks as if some beautiful picture with two triangles intermingled with each other. And I get some crazy satisfaction when I keep on asking this question with the students about the meaning of this symbol. Whereas for the second one, you will directly tell the meaning of this symbol, right? Because you know already there is a Pmos, there is a Nmos. You can directly tell. I feel satisfied when whatever answer I expect, when I don't get it, I get a very crazy satisfaction. Okay, I get a very crazy satisfaction. Anyway, later on I am going to tell you the answer, but I feel happy when you people make a desperate effort to answer my questions. In one way, it is not a Viva question, it is an interview question. To be honest with you, whenever we conduct interviews, whenever we have a particular candidate who is expert in Vlsi, at times I ask such questions only even in the interviews, just to check the understanding level of the particular candidate. Because we have to be always careful when we appoint teachers for our department, right? They should be competent enough to discuss everything, even with basics. That is my intention, that's all, nothing else. You don't have to take me in a negative way. That has been my intention in verifying the knowledge level of the candidates. But with the students, I keep asking such questions only to verify whether you have understood the things properly or not. Because if you understand the things properly, then you will retain this knowledge lifelong. Ultimately, we have to make you as competent engineers, right? That is the only intention, nothing else. Okay, let me not tell about my biography. If you have any questions, you can ask me, or else I'll proceed with the discussion of the layout now. Now you can see the simulation circuit where you will connect input pulse, then you will connect a small load capacitance at the output, so that the load will absorb the signal and load will gradually discharge. Even without the load also, when you start working offline, when you come to the campus, you can actually try out this experiment. This is, even though it's a very simple experiment, it is a beautiful experiment for understanding the basics. In the sense, you can simulate this transmission gate without connecting this load. Then you can simulate the transmission gate after connecting this load. Load is simply a 1 picofarad capacitor there. You can find out the differences between the two waveforms. Anyhow, I am showing you the waveform here. You can see the waveform where you can see a small difference here. You can also see the same difference here, right? Now, there is one input. This is that V in. The lowermost one is V in. And this V in N and V in P, there are two pulses here. Nmos and Pmos are accordingly turned on. Let us say Nmos is turned on here. And at that time, Pmos is also turned on here. Because Pmos gate is 0, Nmos gate is 1. That means logic 1 is there. This logic 1 is transmitted to the output. Pmos passes good 1. Now, when this is becoming 0, Nmos is now off. When Nmos is off, still Pmos is on. So input is 1. That logic 1 is coming here. Later on again, Pmos is 1. When Pmos is 1, still Nmos is 1. Still output is high. When Pmos is 1, Nmos is 1, still output is high. Why still output is high? Because we had connected the capacitor there and the capacitor did not discharge. That is why I had told you that you connect the capacitor and you remove the capacitor, you can check the changes there. Because we had connected the capacitor as the load remained charged. So even in this condition, you can see the output remains high only, in spite of Pmos turning off. Okay, even though Nmos is on, Pmos is off. But Nmos does not pass good ones, right? So the load is stored. But now the question is, what is happening here? Wherever is this blue circle, what is happening here? Here you can see, here input is low. When input is low, Pmos is 1, Nmos is 0. When Pmos is 1, Nmos is 0. NMOS is also off. PMOS also is off. Okay, and input has become 0. And suddenly capacitor discharges to some extent here. Now later on, you can see later on, here when input is low, when Pmos is 0, Nmos is 1. Now Nmos is on, it is passing good 0. When it is passing good 0, Pmos is on, Nmos is also on. So when it is passing good 0, the signal has become completely 0 here. You can see it here. Signal has become completely 0 here. Now in this particular place, you can see a small change. Wherever I have put this circle here, there you can see a small change. That is where the transmission gate is not reliable. Transmission gate in this particular juncture is not reliable because at that time the load will not completely discharge and that may give an erroneous output. It is neither 0 nor 1. For these complications, transmission gate has not yet become completely popular. Even though it is saving power, there is no power consumption at all. Still, we cannot completely implement any design using only transmission gates because of these problems. Okay, that is why we have purposefully put that 1 picofarad capacitor so that you will understand in a no loaded condition as well as in the loaded condition what are all the complications as logic levels we are going to have while we implement transmission gates. So the final outcome is what? We don't use transmission gate only in our design. We combine transmission gate and the static Cmos circuitry together so as to achieve both of our purposes. We want to have a current drive also. We want to have a non-erroneous output also. And we want to have some amount of reduction in power dissipation also. That's why I showed you the diagram of that latch there where we used inverter also and we used transmission gate also together. Now this is the simulation results. Later on we are going for the layout. You can simply connect that Pmos at the top, Nmos at the bottom. Body of the Pmos should be connected to the input itself because that is source. Substrate should be connected to source. And here again, substrate of the Nmos is the P-type substrate. It is the black color screen itself. That orange box at the top is nothing but N-well. But below Nmos is present in the P-type substrate itself. And the substrate is connected again to the source. Otherwise, gate is connected with the Pmos gate is connected with that complemented input of the Nmos gate's input. And later on, you have the regular input signal. And output is taken here at the right side. All those are metal connections. So this is the layout. Layout is really very simple. Then later on, we have to perform this DRC error, DRC check, LVS check, design rule check, layout versus schematic check, and finally we have to go for RC extraction. After the RC extraction, you can see that N-well is completely connected along with the wire. And all the metal layers are completely connected as a single layer. And all the poly layers are also a single layer. This way, this is the completed parasitic extracted layout. Let me see whether you can actually see any parasitics there. No, as this is a very small layout, here we are not seeing any parasitics as such. Let me see whether it is there later on. No, it is not there. So in this layout, we are not seeing a lot of parasitics because it is a simple circuit. There are not many connections. But when you connect multiple transmission gates, you will have parasitics there also. So with this, we are coming to the end of this experiment and the end of today's class also. If students have any more further questions, you can ask us. If I know the answers, I'll try to answer. Or else we will wind up the class. No questions? Okay, if there are no questions, we will stop the class for today. See you in the next lab class. Until then, take care of your health and take care of your studies as well. Deepak, have you posted the attendance link?
In the Google Classroom, sir.
Okay. Then
I
students,
created the observation upload assignments.
okay, fine. Okay, students, today we are stopping the class for now. See you in the next lab class.
Thank
Take
you, sir.
care and bye-bye.